Hi everyone, so in today's Radioactivity lesson 2 we'll be learning about the activity of sources, half-life, techniques and procedures to determine the half-life of an isotope. We'll also be looking at exponential equations again. And we will talk a little bit about how we can use dyes as a simulation of radioactive decay. We might skim through a little bit about the graphical methods and using a spreadsheet of how to use this equation for radioactive decay and a bit about radioactive dating as well. So we'll start first with the activity and we'll progress through it. So before I introduce activity, we're actually going to look at the simulation of radioactive decay using dyes. We use this analogy to help us understand what takes place when we have radioactive decay and how we analyze it. So we're going to assume that we have a large number of six-sided dyes that we can use to simulate the decay of radioactive nuclei. And let's say we're going to pick a specific amount of number because it's going to just make it easier for our calculations. But I will pick 216 dyes. Now let's consider that each dice is a single undecayed nucleus, meaning it hasn't decayed yet. And if I throw all 216 dice, each throw can be taken as a small interval of time. So we have 216 dice, so each dice is an undecayed nucleus. And each throw is a small interval of time. Now we'll consider that when I throw those dice, if one appears on the top of the dice, it means it decayed. So you know how a dice has numbers 1 to 6. So if out of those 216 dice, some of them land on 1, it means that they're nuclei that have decayed. So let's say that 1 shows a decayed nucleus. We also know that the probability of a dice decaying, meaning that of us getting 1 on a dice, is 1 out of 6, right? So the probability of decay, of what we call decay in our model, is 1 over 6. So when I throw the first 216, so for my first throw, when I throw the 216 dice, a sixth of them will decay. So I'll get about 36 dice will decay, which will leave me with 180 undecayed. Now, this is also a good point to mention that we definitely don't, we definitely know that the decay is random, as we cannot predict which dice will decay, but we can only state the probability of decay. So we are simply stating with this calculation the probability of what will be decayed and what will be left behind. Now, after the second throw, so I have 100 undecayed, so 36 decayed, so I'm not interested in them anymore. I have 180 that that have a probability of decaying. So again, 1 in 6. So that will leave me with 30 decays and 150 undecayed. And I can continue doing that constantly until I'm left with a very little amount of dyes that have not decayed. So I can write a general expression of after, let's say, n throws, I will have eventually reached the stage where I will have this expression with how many are left undecayed. Now this is a very constant ratio property. This is something that we have seen in capacitors, where we had exponential decay with time. So we will come across exponential decay here, but before we do, we will introduce a few more terms. So this is very similar to how a radioactive sample behaves. Now there are differences, obviously, because it's a model. In the case of radioactive substances, you're not going to have only 216 unstable nuclei. You're going to have trillions and trillions of them. And the probability of decay, which in this case it was 1/6, actually depends on the real isotope that we're using, because there's different types of isotopes that have different probabilities of decaying, and also they have different half-lives. The half-lives range from fractions of a second to billions of years. This is another quantity that we will be talking about in this lesson. So before I continue, we kind of spoke about and looked at just now the simulation of radioactive decay using DICE. So we'll now go back to activity and half-life and start introducing those key terms. So the first thing is half-life. Now this is an easy definition to remember, especially since you need to link it directly to what is taking place. So half-life is simply the average time, and we use average time because when we look at a graph, sometimes there could be a little bit differences between the timings, and you have to take the average of it, but I'll show that when we do example questions. But yes, average time it takes for half of the number of active nuclei, meaning the ones that are radioactive, in a sample to decay. So if I started with 1 million, for example, so if I had a source full of radioactive nuclei, and there was 1 million of them, so on, after one half-life, half of those would have already decayed. So I'm just going to do like a random. So the empty circles are the decayed, for example, and the full circles are undecayed. So after one half-life, the number of undecayed nuclei n will half. So this is a graph that we usually see. You can clearly see it's an exponential decay. So we start with about 100 grams of worth of strontium-90, which is radioactive. So let's say all of the atoms inside of it are in the 90 grams, in the 100 grams of strontium-90 are radioactive. So how long will it take for that number to half? So that will be us going to half of 100, which is 50. So if 50 grams is radioactive, the rest of them are no longer, the rest of them have decayed. Then I just extrapolate my line, and this is 25 years. So the half-life here is 25 years. I can repeat the same measurement again. So at every single point that I do this measurement, I can always figure out how long it took because of the constant ratio property. So let's say if I go now from half of 50, then it's 25. I extrapolate my line. I see it's at 50. The difference between 50 and 25 is 25. So I can see it will always take 25 years for these specific isotopes nuclei to half. In this case, it's talking about it in terms of mass. Obviously, each radioactive nuclei has mass, hence it will half in the terms of the amount. And as a very quick mention, we usually represent half-life using T and a subscript of a half. So to show that is how long it takes for the radioactive nuclei to fall to half. Not for the time to fall to half, okay? This is a common mistake. So the next thing we need to look at is the activity. Now, activity is defined as the rate at which nuclei decay, meaning how many decays we have per second. So if I were to write an equation for activity, it will be the number of decays per unit time. Usually, obviously, the number of decays doesn't have a unit of its own, but time does. If I use time in seconds, then the unit of measurement for activity is becquerels. If the time is in hours or days or years, then the unit won't be becquerel. So if you are calculating activity, it needs to be definitely in seconds for you to be able to get it in becquerels. So for example, if I said the activity of a radioactive source is 2000 becquerels, that means 2000 nuclei have decayed per second, or you can equivalently see it as 2000 alpha particles. In this case, if it was an alpha particle source, then 2000 alpha particles were emitted by the source per second. And very importantly, it specifically depends on the number of undecayed nuclei in the substance and the half-life of the isotope. In this case, we have seen this and how it worked in dyes. So we saw how as I was going from the one throw to another, so here we can see it, from one throw to the next. So the initial one, we had more more nuclei decaying, but as less and less radioactive nuclei were left, we had less and less decays for each unit of time, because we remember each throw was supposed to represent a small interval of time. So as a radioactive source decays, its activity drops with time as well, as it's expected. So now that we have introduced activity and we saw how it kind of works in terms of the dyes and similarity, we can consider a very large number of atomic radioactive nuclei, n, at time 0. Oops, it. If time 0 we have n undecayed nuclei, then we can assume that in an interval of time delta t, that there are a number of nuclei disintegrating, so decaying, and that should be directly proportional to both the number of nuclei present and the time. So we assume that delta n is the decayed nuclei. It should be directly proportional to the number of undecayed nuclei, just like we showed in the previous part, and the time that the small amount of time that it took it for it to disintegrate, to decay. So I can rewrite this equation. I'll just rearrange it to delta n over delta t, directly proportional to the number of undecayed nuclei. This is a direct proportionality relationship. We have already defined this to be as an activity. So this is the number of decayed nuclei per unit time, just like we see in activity here at the top. So in other words, A is directly proportional to the number of undecayed nuclei, so activity is directly proportional to the undecayed nuclei. Now the constant of proportionality in this case would be the decay constant. So A is equal to lambda n, where lambda is the decay constant. So yeah, here I was supposed to put a minus sign as well, just to, even though we're ignoring the minus sign later, the minus sign here is to just simply represent the fact that the number of undecayed nuclei decreases. And in the case of the decay constant, we can consider it as the probability of decay of an individual nucleus per unit time. So it does have a unit, and we need to make sure that we are confirmed with our units, that they're balanced on both sides, that it's a homogeneous equation. So just to mention it here, n doesn't have a unit. Activity has a unit since it's the number of decays per unit second is becquerels, but it is still per unit second in SI units. that means that lambda will also be, so the decay constant will also be per unit second, since there are no units for n. So it is the probability of decay. Probabilities don't have units, but per unit time. So that part of it can help you remember it if you don't remember it in terms of the definition. In the actual exams, you will be given both this equation and this equation. I will go a little bit more into detail after that for this, but yeah, you definitely should be able to understand what each one means and how to use each one. The common thing that many people get confused with is that this is the decayed nuclei and these are the undecayed nuclei. Okay, so far we've spoken about the activity of the source, we introduced the decay constant and the equation. We did speak about the half-life, but we haven't yet seen the equation, which we will get to. And I will move on to the next few bits now. So for this part, you do not need to know. I'm just simply going to derive the equations that you will be given and should be able to use. But in this case, you do not have to know it. It's just if you are interested to link your mathematical integration knowledge into this. So in this case, we have the relationship that we already spoke about, the number of decays divided by the specific amount of time interval is equal to the decay constant times the number of undecayed nuclei. So if I want to solve this equation, I have to take infinitesimally small time interval and nuclei. I will rearrange it to leave dn and dt on their own, and then I will take n to this side so I can match the dn on that side. So I will divide both sides by n for that. So this is the expression I have come up to so far. Now I can integrate both sides. And since I'm integrating with respect to time here, is then at time 0, I should expect to have n naught radioactive nuclei. And obviously as time goes by, at time t, I should have n radioactive nuclei left. When I integrate with 1 over n, then that will be ln n and n naught. So those are my limits. And that will be minus lambda t, these limits. So I have ln of n minus ln of n naught is equal to minus lambda t. Since t 0 times lambda is 0, then I will ignore that bit. And I can combine these two from the logarithmic rules. So that will be ln of n over n naught is equals to minus lambda t. Now this is when I can raise it to the power of e. And if I do so, e ln cancels, so it will be n over n naught is equal to e minus lambda t. Once again, for you how to deal with this, if you raise it to e ln n naught, this cancel and you're left with n over n naught. This is also given to you in the formula booklet. You do not need to know this once again, but if you are interested to do, then you can. And just rearrange it and come up to this expression. So you need to know how to use this equation. You do not need to know how to derive the equation. Also equivalently, since we know that a is equal to lambda n, if I rewrite this expression here in terms of A. So I'll multiply both sides by lambda, that will give me A, but obviously they cancel. So I will have the same expression for activity. A is equal to A naught e to the minus lambda t. So these are the two expressions that you are given and you should be able to use, and I will go through them anyway in a little bit more detail. So what equation did I actually derive? It's an equation that tells you the number of undecayed nuclei after a time t, after this time t that you will insert there actually, more specifically, which is equal to the original number of undecayed nuclei times 0, times the e, which is the base of natural logarithm, to the power of minus lambda, which is the decay constant, times the time that I want to know how many nuclei were remaining after. Like I already said, since activity is directly proportional to the number of undecayed nuclei, I can also use the equation A, which is the activity of the source after a specific amount of time, is equal to the starting original activity times e to the minus lambda t. So similarly, instead of number of undecayed nuclei is the activity. So from here, we can figure out how the decay constant and the half-life are linked together. So I will use the first equation only. I don't need the activity one. So if I want to know what's going to happen after one half-life, then this t will be equal to the half-life. And I know that n after one half-life should have halved. So it should be half of the original starting number of nuclei times 0. So n, in other words, will be n naught over 2, because I know that after one half-life, the number of undecayed nuclei halves. So now I'm just going to substitute those expressions in here. N naught and n naught cancel out, because if I divide both sides by n naught, they will cancel out. So what I have left is a half is equal to e minus lambda half times a half-life, so the decay constant times a half-life. This is when things get nicer, so I can take the natural logarithm of both sides. Now this will cancel. I will be left with this expression. Once again, for this one you do need to know it, but in this case you can find the rules of logarithms when you're multiplying them or dividing them and so on. Now, based on those rules, this means ln of 1 minus ln of 2. But if you put in your calculator, ln of 1 is 0, so we're left with minus ln of 2 is equal to minus lambda t a half. So I can get rid of all these nasty minuses from here because they make my work look a little bit messy. And I end up with the expression of decay constant times half-life is equal to ln 2. So this is a constant expression that you will be using throughout, where you have decay constant times half-life. And remember, the decay constant has a unit of per second. Half-life has a unit of seconds, or depending on what you're using, actually, you could use, as long as they both have the same equivalent units. So if it's one is per second, the other one has to be in second. If one is in hours, the other one has to be in hours, and so on, or years, and so on. So this will be in second, and then the other one is a number. It doesn't have really a unit. So the biggest thing that you can gather from this equation is that the decay constant and half-life are inversely proportional to each other. And it also depends on they depend on each other as well. So the half-life depends on the decay constant. So the probability it takes per unit time for something to decay. Okay, so this is an example. As I'm reading through it, I will start making a list of my values to understand what the situation is. So we have a sample of thorium that has so many nuclei at the start, meaning that that's n naught, the undecayed starting amount of nuclei. It gives us its half-life, which is 18 days. And it's asking us to calculate its activity after a time of 22 days. That means that if I need to find the activity after a certain amount of days or time, I know that activity is A naught E minus lambda T. I do not know yet the lambda. I don't have the decay constant. And I also do not have the original activity yet. So I will need to take into account how I will be able to calculate those values, right? That could simply be A, L naught, lambda N naught, because the initial activity can be based on the original number of undecayed nuclei times the decay constant. We already learned this equation before we learned this one. So I need to make a few calculations here. So I need to find lambda. We already said that lambda can be calculated in the last step by ln of 2 divided by the half-life. I do not necessarily have to change my units yet, so I don't have to change my days into seconds, but if you would like to, you're more than welcome to. I will keep it constant because I can cancel out the days after instead of converting it, since it gives me the half-life in days and the time after 22 days what will happen. So we'll keep it at a constant value. So lambda is ln of 2 over 18. I'm going to leave the d there for me to remember that is days. Actually, it's wiser for me to change it because I need to use it for the activity and it won't work otherwise. So anyway, it's going to be 18 days times 24 hours times 60 minutes times 60 seconds. And that will give you a value of about 4 so lambda is 4.457 times 10 to the minus 7 per second. And that way I can calculate the activity now. So I can use this n and naught to calculate the activity. So A naught will be lambda times the original number of nuclei that are undecayed. So my activity will come up to 1783 times 10 to the 6 becquerels. So that's my A naught. So I have A naught now, I have lambda, and I do have the time as well. In this case, I can still kind of cancel out the timing if I want to, just to make my life a little bit simpler. So A will be A naught, which is 1.783 times 10 to the 6, times E to the minus lambda. Lambda is ln 2 over 18 days, times T, which is 22 days. So here, this is why I said before, maybe you don't have to, but obviously because we did the activity, we had to change into seconds. But here I don't have to. I can simply simplify it. And once I place that in the calculator, you will get an activity of 7.6 times 10 to the 5 becquerel. So you can see that after after a little bit longer than a half-life, you have the activity dropping already, which you should expect. If you got something bigger, it means you've done something wrong in your calculations. So coming back to our learning outcomes, we have now finished looking at the half-life and that equation that involves half-life. Um, we have also looked at the the exponential equations, where we also derived it, if you are interested in that. We have a few more things to look at. Just before continue, a little bit more about the decay constant. So if you have a large decay constant, then there's a high probability of a nucleus of an isotope decaying. So every single isotope has its own decay constant. Now, if it has a high, we said, then it means that there is a high probability for a nuclei to decay. So it will take it a shorter time for all the unstable nuclei to decay. And for activity to fall to zero. However, if the decay constant is low, so it means that the probability of decay each second is low, then it will take it a much longer time for the unstable nuclei to decay. So it will take also longer for the substance to stop being radioactive. I'll just reword what the significance of lambda is in that case. Also, you should be able to, even though it doesn't clearly state it here, you should be able to link these two equations to the equation of a straight line. The only way to do that is we take the natural logarithms of both sides. So it will be, so for a, so if I take the natural logarithms of both sides, I end up with an expression of ln A is equal to ln A naught minus lambda t. Once again, this is how I'm multiplying it. Ln E cancels and you're left with minus lambda t. So if I wanted to plot this equation to get a straight line, so otherwise this expression here gives you an exponential decay, and you already saw that even in chapter of the capacitors chapter. So if I wanted to plot this as a straight line, then I will have to plot ln of A against t. It should be a straight line, but we'll figure out what straight line and what the gradient will look like just by trying to link the equation to y is equal to mx plus c. So if my y is ln A and my x is t, so I'll just write it as minus lambda t plus ln of A naught. And now I can link my values together. So y is ln A. My gradient is minus lambda, since x is my t. And my y-intercept is ln A naught. So it will have a point that's A naught here. And it will be a straight line with a negative gradient of that's equal to the decay constant. So you should be able to relate these things together, even though they're not explicitly stated in the specification. It is specifically stated that you should be able to link any equation or that you have learned, or even random ones, to the equations of a straight line. So it's all about rearranging, linking what your y and x axis will be, and then how that link to y is equal to mx plus c. Okay, so the next thing that we'll have a look at is the techniques and procedures used to determine the half-life of an isotope, such as protactinium. This is actually a pack that we tend to do in class, but due to restrictions now we can't. So I will just describe the experiment briefly, and then we'll move on to the next part. So in our labs, we usually use protactinium generator as our radioactive source. Is what you actually see in the picture here. So this is where we store it. So this is the radioactive source. It's stored in here for safety. It's got like this little cushiony thing as well, and also double layer of plastic to absorb any radiation that might escape from it. It's also stored very safely in a safe in our school. But yeah, we basically open this only. We take this out. The protactinium generators are radioactive source. You can see that they also have the signs on them as radioactive sources. We need to ensure that we have safety features. So we're wearing goggles, ensure that the generator bottle is not damaged. So this bottle, we need to make sure that it's not damaged anywhere around it. It's better to hold it either with tongs or mostly gloves actually we use, and as far away from the body as possible. You need to wear a special lab coat, goggles, gloves. Do not attempt to open this, obviously. It's very dangerous. And when we do shake it, because we have to shake it to activate it, it doesn't mean that we activate it. I will explain that when we go through it in class. You don't need to know too much detail about it. You just need to know that we need to shake it, but we have to do it over a tray. So basically what is going on inside there is that it has uranium-238 that decays by an alpha decay to thorium-234, and then thorium-234 decays by beta decay to an isotope of protactinium-234. Obviously, when we measure the decay rate or the decays from this experiment, we cannot measure alpha decay because it gets absorbed by the plastic, since alpha particles can get absorbed by a little thin piece of paper. They definitely get absorbed by that. So what we are measuring really is beta decay when we're measuring the counts. From the picture, you can see the setup. So you have your radioactive source, you have your Geiger-Müller tube or Geiger counter, and you have your rate meter, or you could connect it to a computer to make the measurements. Now the first thing that we will do is we will take, that we do in the experiment is we measure background rate, background count rate, if you want to call it, without the source present. So we need to remove the source from here away so that we can get an accurate measurement of the background radiation. Then you shake the bottle for about 10 to 15 seconds so that the protactinium dissolves in the organic solvent. And then we face the Geiger-Müller tube in the opposite side of the organic layer, just like you can see here. So the Geiger-Müller tube is pointing at the organic layer of the protactinium mixture. You will need to then take the counts from the decaying protactinium every 10 seconds. So you record it for about 10 seconds every half minute. So record counts for 10 seconds every half a minute. When you look at the screen here, basically tells you the counts here. So it will be increasing, but it's not actually increasing because you're going to have to subtract the previous measurements. But obviously I can't explain it too well unless we do the experiment and do the calculations together. So you will need to be quite quick. Previous years we were recording the actual experiment with a mobile phone just to make sure that we get the correct readings at the correct times, just in case it moved too quick or anything. And it worked quite well. And then when you do the experiment, you need to get the corrected count rate by subtracting the background count rate from it. And when you plot a graph, you can get the half-life of protactinium by looking at how long it took for the activity to halve from the initial time. And since protactinium has a short half-life, so about just a little bit more than a minute, about 70 seconds if I remember well, it's easy to get quite good results by repeating and plotting it. Okay, so we have looked at techniques and procedures to determine the half-life of an isotope such as protactinium. Now, a few points left. This is a bit hard to do through a video, but I'll just briefly go through it only. I won't spend too much time on this. And then we'll look at radioactive dating as well. So here what you require to basically be able to do it is a modeling of radioactive decay using spreadsheets is to get quite close and similar results to what would the actual equations will give you if you were to do the calculations using these equations. So they're extremely good. The iterative method modeling that we also seen in capacitors is really good, and can even improve better if you use smaller time intervals. So first thing that you definitely need to start with is the number of undecayed nuclei in the sample to begin with, and not. You need to also choose a very small time interval. So basically you will know n naught. You will decide on a very small time interval that's much smaller to the half-life, because obviously you need to be able to assume that the activity of the source doesn't change significantly in that small time interval. So you will be able to pick your small time intervals in that case. Then the next step is to calculate the change in the number of nuclei, basically the number of nuclei decaying during that interval delta t, by using this equation. This is basically a rearranging of the equation that we have seen previously in this lesson. We're ignoring the negative sign only and only because there was supposed to be a negative sign, but we're ignoring it only and only because we included the negative sign in our definition of delta n as the number of nuclei decaying. And then for the fourth step, you can calculate the number of undecayed nuclei in the source at the end of period delta t by simply subtracting the change in the nuclei from step 3, so what you calculated here, from the previous value of n. And then you keep, for the fifth step, you keep repeating for the fourth step for the other multiples of time intervals delta t. So you definitely be given also the half-life for something like this to be able to be calculated, so that you can obviously find lambda. Remember, or you can be given lambda directly as well. Yeah, that's basically all you need. And then you create a spreadsheet, and if you compare the values that you get with the iterative modeling method and the values that you get by using this equation, they're so close to each other, but they even get better and better if you end up choosing to use smaller time intervals. So if you chose to use, I don't know, 1 second time intervals, and then you decided to change it to 0.1 seconds, obviously you'll get a better modeling method for it. So just going to keep that brief because it's too much to go through. Unless we were doing it on a computer, then it would be much easier. And the last thing that we will look at, so we spoke about this now. The last thing that we're going to talk about is the radioactive dating, like carbon dating. Okay, so we're going to start first with, in terms of radioactive dating, we're going to look at carbon dating. Now, we all have carbon atoms within us. We are carbon-based life after all. And it mostly starts from plants, because plants take in carbon dioxide, where they take the carbon in, and then it goes up the food chains and the food web. So animals will eat plants that have carbon, then they will take on that carbon, and then other animals will eat those animals and they will take in that carbon, and so on and so forth. So we know that the atmosphere contains mostly the stable carbon-12, but there's also isotopes of carbon, such as carbon-14. In nature, we are assuming that the ratio of carbon-14 to carbon-12 nuclei in the atmosphere is constant, even though we know that it might not be. We are assuming that it's about, sorry, that's not to the power, that's 1.3 times 10 to the minus 12, the ratio of carbon 14 to carbon 12. So you can see that there's much less carbon 14 isotopes on that. And like I said, we are assuming that the ratio is the same in all living things. Now, when an organism dies, it will stop taking in carbon. So that means that even though the carbon of 14 it contains continues to decay, so will the ratio decrease over time as well. So we take the activity from a carbon 14 in a sample of organic material like a tree or a body that's decaying. So if we get the activity, then we definitely know it's directly proportional to the undecayed nuclei in the sample. So in that way, we can calculate the time since the organism has died by comparing the activities and the ratio or the ratios of the carbon 14 to 12 nuclei of the dead material to the similar to a living one. So we call this carbon dating. So carbon dating can happen for organic materials as about old as 50,000 years. However, and this is possible because the carbon 14 half-life is about 5,700 years, but there are limitations to this method. So some of the limitations is the fact that the quantity of carbon 14 is extremely small. So that means that the count rates are correspondingly small, and after a few half-lives, it might be really hard to distinguish it from the background count rate. So that makes it really hard to get the age of older and older objects or, well, in this case, organic material. And also the ratio of carbon 14 to carbon 12 in the air and in all living things is assumed to be constant and that there will be no change over time. That can't be true if there have been changes in the rate at which carbon 14 is produced in the atmosphere. So those are the two limitations. So firstly, it will activity will get so small that it is indistinguishable. So that's the limitations. And another reason is, like we said, we are assuming carbon 14 to carbon 12 ratio is constant. However, there could be changes in the rate at which carbon 14 is produced, so that could change with time. So we'll go through an example for this. It's talking about a wooden axe that was found in an Egyptian tomb to have an activity of this much. Oh, sorry. The activity on identical mass of wood cut from a living tree is this much. So now we are identifying some values. So basically it's telling me that the original activity of a similar wood is 0.65 becquerels. But the one that we found in a wooden tomb sorry, is 0.38 becquerels. So obviously after the years, the activity of carbon 14 has decreased. Calculate the age of the wood. So we need to find how long it took for the activity to drop. If carbon 14 has a half-life of 5,700 years. So we know the half-life of it. So just to remind you again that lambda times half-life is equal to ln2. So we can always use that since we need to definitely use this equation. I need to calculate lambda. So I need to make sure that I change my half-life into seconds. So that's years, that's days, that's hours, and that's for the seconds. And you will get something around 3.84 0.48 times 10 to the minus 12 per second for the lambda. And then you can use the equation to determine t. I'm not going to put any values in yet until I make sure t is the subject of the formula, otherwise it will start looking messy. So once again, you take the logarithmic of both sides. Actually, I'll rearrange it a different way. I'll leave the t to be positive, so I'll bring the t on the other side. Lambda t will come here, that will be ln a naught minus ln a, which is ln a naught over a. And then I'll divide my expression by lambda to get t. And then I can put all my values in, so t can be 0, sorry, that's, yeah, ln of 0.38 over 0.65, sorry. Divide that by the lambda, and that should give me a time of 1.395 times 10 to the 11 seconds, or if I change that time to years, the time will be about 4,400 years. So that's a very old axe, wooden axe that was found. So like we mentioned again before, this technique assumes a constant ratio over time. However, that can be reduced to increase the emission of CO2. There's a lot of fossil fuels being burned, so definitely CO2 in the atmosphere has increased. There's also a lot of testing of nuclear bombs, and that makes it even add more to it. And like I said, there's extremely small activity, so it will be easily comparable to the background radiation. It will be hard to distinguish between them. So what do we do when we can't distinguish between them? Can we proceed for something that's older than 50,000 years? Well, how do we date rocks? Dating rocks, not going out on a date with them. And we also know that rocks on Earth or meteors formed during the creation of our solar system are far too old for us to even be able to use carbon-14 dating, which has a very short half-life compared to the age of those rocks. So what do we use instead? Geologists use the decay of rubidium-87, whose half-life is longer than the age of the universe, which by the way is assumed to be roughly 14 billion years. We will actually calculate it ourselves as well, but as a rough estimate, it's about 14 billion years. But rubidium has a longer half-life. Rubidium-87 has a longer half-life than that. It's used to date rocks on Earth and meteors. Like I said, carbon-14 is obviously not suitable because it has a much shorter half-life, and it will be so hard to distinguish between background radiation at those kind of ages as well. Okay, so that was it for the last learning outcome. We have completed all of them. If you do have questions, please do let me know.